Okay, so let's continue with the last step in the lithography process, the development step. So we're going to talk about the principle of development and what kind of effects we can see from development. And then we're also going to talk about the different, some more things that are related to the properties of the resist itself, and go into more detail about that. So the development process is basically we want to go from the latent image in the polymer film from the exposure to a real physical image in our resist masking material. So what we do is that we submerge our resist in the developer, and the developer dissolves part of the resist. So then we can rinse and dry, and we are left with a pattern in the resist film. So you can see some of the equipment that we can use here. Manual developer baths and spin dryer, and then we have this nice machine here that does everything for us in one go. When we talk about the principle, I'm just listing again here what we have in the photoresist. So there is the resin, the photoactive component, and the solvent. But by the time we come to the development step, we have actually already removed the solvent in the soft bake, and we have activated the photoactive component in the exposure. So something has happened during the exposure which has changed the solubility of the resist in the areas where it was exposed, which means that the developer will then dissolve some resist, but not other parts of it. In some cases, the photochemistry is kind of like a catalytic process, which means that the light initiates the process, but it then has to be finished by some thermal energy in a baking step that we call post-exposure bake. So in some cases, you need to go from the mask aligner, you need to go to a hot plate before you actually go to the developer. The methods that we use for development is submersion development, which is where we have a large bath of developer, and then we just put the wafer in, and you can actually put several wafers in at one time. And then we have the alternative to that is the puddle or the spray developer, where we run them one by one and deposit a little bit of developer on top, much like what we did in the spin coating process. So you actually dispense the developer on top, so that's the puddle developer. You dispense developer on top of the substrate, leave it there for some time, and then spin to get it off, and you can rinse with water afterwards. And then there is the other one, the spray developer, where you are creating a mist of developer and spraying it onto the substrate, and typically continuously throughout the development time. In some cases, this is necessary because the resist actually requires kind of like a chemical-mechanical combined attack in order to develop. Yeah, we basically only have submersion and puddle developers here at Danchip. Okay, let me show you a video of our automatic puddle developer in action. So this is a robot and very similar to the spin coater. But you can see instead of resist, we actually get a developer liquid on top. And now you can see it slows down and then creates the puddle. And you can probably already see the pattern emerging now. So the resist is already being dissolved. And after some time, we can spin off. And then there's a rinse with water. And at the end, there is a rinse with nitrogen from the top. So you can see it's dried completely. And when it stops, you will be able to see that there is actually a pattern on top. So this is similar to the pattern that was on these wafers here. Okay. So I just want to talk about a term that is called resist tone. So we have two different kinds of resists, basically. It's two different types of resist, positive tone and negative tone. And if we start with the positive tone, we spin coat a layer of resist on top of the substrate, which is not soluble in the developer. So that's where we start. We start with something that would not dissolve if we put it into the developer. And then we do the exposure step, and in the exposure, the photoactive component is activated by the light and changes the solubility of the resist so that it becomes soluble in our developer. So that means when we actually put it into the development process, the parts that were exposed to light are now dissolved and removed, so we are left with the positive image of the mask in our resist film. On the other hand, we have the negative tone resist, where we actually start with a layer of resist coated on our sample, which would dissolve completely if we put it in the developer. So this is now soluble polymer. Then we expose it to UV light. This activates the photoactive component, and the photoactive component changes something in the resist and makes it insoluble in the developer. So typically what happens is that the resist chains will cross-link due to the photoactive component, and this typically means that we require a post-exposure bake between the exposure and the development. So that means we now go from, let's say, short polymer chains that would dissolve in the developer to basically one big molecule because everything cross-links together. And this does not dissolve, so when we put it into the developer, everything else except what was exposed is now removed, and we are left with a negative image of the mask on our sample. So that's the difference between the two. So again, in the positive tone, what you expose becomes soluble, and this is typically done by some kind of change in the polarity of the resist so that it reacts better with the developer solution. It can also be that the light actually, or the photoactive component maybe, actually cuts the polymer chains into smaller sections, which means they are more soluble in the developer. And for a positive resist, bleaching during exposure, so that means where we actually sort of change the absorption as we expose, makes it possible for us to have straight sidewalls even in a thick resist. Because we can sort of, so the problem is that if you have a very thick resist, you have to expose for a long time in order to actually expose the resist at the bottom, so near the substrate. So that means normally if there was no bleaching, the top half of the resist would be overexposed. So you would get some kind of angle in the sidewall because it basically reacts more to the light that sort of leaks out into the resist. But if you have bleaching, then you can limit this a lot, and you can get the straight sidewalls even in a thick photoresist coating. For the negative tone resist, the exposed resist becomes insoluble in the developer. This is typically cross-linking, but it could also be polarity change, just with a reverse effect as for the positive one. And the cross-linking ones, usually, they would require a post-exposure bake, usually. There's a special case in that one of the negative resists that we have, the one that's called NLOF, actually exhibits no bleaching at all. So there is always a difference in the dose, in the actual dose that the resist receives near the substrate compared to on the top of the resist. And that translates into a fact that we always get negative sidewalls. So if we expose and we have resist left in the center, it will be smaller, the footprint will be smaller than the top of the resist. I will go into detail about why this is in a later slide. There is a couple of special categories of photoresists. One is called image reversal resist. So this is basically a resist where you can choose by how you process it, whether it's a positive tone or a negative tone resist. So it's a positive tone resist, but you can choose to do something to it and change it to a negative tone resist. So what happens is that we go through the two first steps as normal. We coat the substrate and we expose the resist through the mask. But then we add a baking step, which then activates a crosslinker in the resist that reacts to the areas that were exposed to the light and crosslinks them, which means they are now insoluble. So now we go from everything soluble before the exposure, then during the exposure, nothing is soluble before the exposure. Then we expose and make the pattern soluble, but now then we bake and make it insoluble again. So we are now left with something that wouldn't develop at all. So we need to add an extra step of exposure everywhere in order to make all the parts that we don't want soluble in the developer, so that when we develop, we end up with a negative image of the mask. So this is, we have one resist that can do this trick. And another category of resist is the ones that are called chemically amplified resists. So this is the ones where the photoactive component is kind of like a catalyst. So when you add heat, it actually reacts with the resist. This is something that is used in industry in order to sort of split the dose between the exposure equipment, which is usually the bottleneck, the one where the throughput is limited, and then sort of you move part of the dose. That means it means that you expose for a shorter time, and then you add some energy in form of heat later on in order to get the full dose. So this is something that is used in industry to increase the throughput. So you can have only one expensive stepper machine, and then you have a lot of inexpensive baking machines afterwards. So that's how you do that. For us, it doesn't make much of a difference. We just need to keep it in mind that if we have a resist, we have to think about whether it requires the post-exposure bake after the exposure, but before the development. The developer chemistries that we use at Danchip are listed here, and I'm just going to show you these symbols as well. The image reversal resist uses the sodium hydroxide based one, which is called 351B. And the newer resist that we have use the TMAH based one, which is called 726. And then there's SU8, which has a solvent-based developer. So this is really special to all the rest of it. But when you see here our list of resists, you can see that we have a strictly positive one here. So this is only positive tone, and it is made for this developer. But I have actually heard people who are using the old one as well. The negative one, the NLOF, is purely negative, and it uses this one. I read somewhere that it works with the old one as well. Then we have the image reversal resist here, which you can see is both positive and negative. And this works perfectly well with both cases, in both cases. So the 351B is the one we use for submersion development, and 726 is the one we use in the puddle developer. But this one can be processed in both without any problems. And the same goes for this resist, which is a purely positive, thick version of this image reversal resist. And it also works in both developers. And then we have SU8, which is always negative and only uses this particular solvent-based developer. Okay. So I want to go into a little bit of detail with the photochemistry because it actually has some consequences when it comes to the processing. So the one that I'm going to talk about is the one that is in our positive tone resists. And it's based on this DNQ sulfonate molecule, which, oh, I jumped ahead there, but it looks like this one here. And when you add UV light to this molecule, this guy out here breaks off and becomes nitrogen. And then if it is allowed to absorb some moisture, then it transforms into a carboxylic acid. And what happens here is that the resin itself has a limited solubility in the developer. But when you add the DNQ, then the solubility is lowered. Yeah. So it becomes less soluble when you add the DNQ. And then when you transform the DNQ molecule into the carboxylic acid using UV light, then it becomes much more soluble in the developer. So you can see it's a positive tone resist. We go from low solubility to high solubility by adding the UV light. But it also means that we need some water. There has to be an H2O molecule for each transformation of DNQ into the carboxylic acid. And when you do the spin coating and bake, do the soft bake, then this is completely dry. This happens at around 100 degrees, so there's no moisture left in the film. So you need, for this type of resist, you actually need to take into account that sometimes you need a little bit of a time, a little bit of a break between the spin coating and the exposure in order to make sure that the water is inside the film again. So this is something that for a 1 or 2 micron film happens in seconds. So don't worry about that. But if we are using one of the thick resists, the one called 4562, which typically does 5 to 10 micron layers, then we need to make sure that we give it at least 10 minutes or so between the two processes. Otherwise, we can get the problem that it doesn't really develop all the way through because the light was there, but the water was missing, so the process didn't complete. There is also the other thing. So one thing is that it needs the water in order to complete, but there is also the other thing that we actually produce nitrogen inside the resist film. And if this gas is not allowed to diffuse out, then it will actually clump together and create bubbles. This is especially if you have some kind of heating between the exposure and the development. So this is typically the case if you do the image reversal of the 5214E. So there you need the baking after the development, and if you do that too soon, the nitrogen is not allowed to diffuse out. And For some reason, nitrogen is actually diffuses out slower than moisture diffuses in. So this is actually something that happens not in seconds, but in minutes. And if you go to thick films, it actually requires maybe hours to finish. So it's something to keep in mind, but only if you're using a thick resist. For the negative resist, like the NLOF and the SU8, there's a completely different photochemistry, and there's no need for rehydration or outgassing. So that's not a worry in these processes. Okay, some effects that we can observe after the development. A typical one is under development. So we didn't have enough time in the development to actually remove everything. So there is a thin film of polymer left between all the structures that we wanted. And that will typically show up as some kind of coloring of the substrate between the structures. So this is a thin film of resist which creates an optical effect of coloring the substrate. So the way we can get rid of this is by increasing the development time. And in the case of a positive tone resist, we could also increase the dose. So in some cases you will see that even though you continue developing, it still doesn't go away. And that basically means that it's not something that has to do with a limited resolution rate. It's basically that the bottom part of the resist was never exposed, so the dose was too low. Another thing that we see is what we call dark erosion, which is that the pattern that's supposed to remain is actually attacked by the developer. So this can have the effect of making our resist film thinner, and also typically makes all of our structures a little bit smaller. And what we want here is to minimize the development time. And for positive resist, there is some effect in optimizing the soft bake parameters. In some cases, if there is a little bit of solvent left in the film, this can react with the developer and actually create a carboxylic-like acid, which means that now the resist behaves as if it was exposed, so it starts to develop even though it had no UV light. For a negative resist, usually what we have to do is to increase the exposure dose, because it basically means that the cross-linking wasn't fully finished because the dose was low, and that means the developer will still eat the exposed areas. Another thing that we sometimes observe is scumming. So this is basically where there is like a layer of, typically looks like a bit like a foamy stuff left behind in between the structures. So this is something that would be on the substrate after development, but like a thin film of something left there by the developer. This is very dependent on the substrate and the developer. Well, actually the substrate and the resist and the developer that you use. So there's some people will see it and some people will never see it. And I never really put what we do to get rid of it, but the only thing we can do, if we cannot optimize the procedure to get rid of it, then we need to basically etch it away in an oxygen plasma after the development. If we forget to do post-exposure bake in a process that actually requires it, this has some effects. If it's a positive tone resist, it will generally look as though the dose is too low. So that means we get under development. So we will see that even though we develop for the required time, and even though we develop even further, we won't see full development. For a negative tone resist, it's actually a little bit worse, because that means that the cross-linking doesn't happen, and that means that everything disappears in the developer. So if we forget the post-exposure bake for a positive resist, it's back to square one, coat and expose and develop again. In a positive resist, you can sometimes solve the problem by just developing a little bit more. Okay, so now let's return to this to the negative resist that has no bleaching. So this is the Enloff resist, which is typically has this procedure, or has this, sorry, this property. So if it's a negative tone resist that cross-links, then the rate at which the cross-linked areas are dissolved in the developer depends on the cross-link density. So if it's cross-linked to a very hard material, it doesn't dissolve at all. But if it's only partially cross-linked, it still has a finite development rate. So when you combine this with a resist that doesn't bleach, which means that there will always be a higher dose on top of the resist compared to at the substrate, then you get a gradient in the development, a gradient in the cross-link density down through the resist film. The top part will not react a lot to the developer, but the bottom part will react, so you get the negative sidewall. So that's why we get something that looks like this. So again, the erosion rate is higher near the substrate because the dose, the effective dose was lower there. So we get this that kind of profile after development. Sometimes this can actually limit the resolution, because if the footprint becomes so small that it doesn't stick to the substrate anymore, then it just goes away. And we have the problem that even though the resolution of our lithography process is high enough to achieve this, then the adhesion is not strong enough to keep the structure there. Okay. The last thing I'm going to talk about when it comes to photoresist is the contrast of the photoresist. So ideally what we want in a photoresist is that everywhere it's exposed, everything goes away, and where it's not exposed, everything stays, right? That's for a positive tone resist. So this is generally what we want, and we want the transition to be very sharp because we want a straight sidewall between the two. In the ideal case, that's what we want. But of course, in reality, what actually happens is that if you give it a very low dose, nothing happens at all. And then at some point, something starts to happen. And at an even higher dose, everything happens so that we get development all the way through. So that's what you can see here in this graph. You can see here that in the beginning, nothing happens. Then something starts to happen, and here at this dose here we get a full development. So we just need to be at this dose to get the desired property. But then for another resist, it might look more like this, so that actually something starts to happen, a little bit starts to happen already in the beginning, and then finally it picks up speed and finishes here. And the slope of this part of the curve here is what we call the contrast of the resist. Actually, you can also see in this graph, you can also see dark erosion, because you can see that even though, so what we are seeing here on the graph out here is the thickness after development divided by the nominal thickness. So if we measure the thickness before development, and then we develop even without any dose at all, and measure the thickness again, there is sometimes a difference because of the dark erosion of the unexposed resist. So the question now is, what would this contrast curve, what would it look like for a negative tone resist? So do you have any thoughts on that?
It would be like an upward slope.
Yeah.
So the more we expose it, the more will remain.
Yeah. So we start with nothing remaining, right? And then it goes up and everything remaining. Yeah. So it's just reversed like that, right? So for the negative tone resist, which is just reversed. We need some kind of dose in order to get the cross-linking starting, and then we will see that it increases with the dose, and finally we get everything remaining. So the formula for the contrast is basically the same, just the definition of the 2 points that we used are different. So in contrast, low contrast versus high contrast, if we look at at the latent image that we have of our mask that we have in the resist after exposure, you can see here that what we normally want is this down here, where we have a kind of like a step function in the resist afterwards. So this is achieved by a high contrast, but if you go to a low contrast, then you will see a more sloped effect like this one. So it more closely actually represents the actual intensity distribution inside the resist. So in most cases, what we want is a high contrast. The contrast of a resist depends on a lot of things. There is, of course, an inherent contrast in a resist chemistry, but it also depends a lot on what kind of developer you're using. If it's a fast developer, you usually get a low contrast. Compared to a slow developer, you can get a much higher contrast. And there's also some effect of the soft bake because of the effect that the soft bake can have on the dark erosion. And all the other things that can influence it.